Everyone, and welcome to the Open Science Seminar of the Italian Reproducibility Network, that is supported by Italian Association of Psychology. Today, we have the pleasure to host Dr. Alexandra Sarafoglou, postdoctoral researcher at the Psychological Methods Unit at the University of Amsterdam. Alexandra's interests lie in psychological research methods, cognitive modeling, Bayesian statistics, and open scientific practices. Specifically, her work aims to investigate reform ideas such as pre-registration, analysis blinding, and the multi-analysis approach, which address the reproducibility crisis. Alexandra developed Bayesian statistical methods to support researchers in their work. She also serves as a board member of the Dutch network of open science communities, and she has been a steering group member for the Dutch Reproducibility Network. The last part of the seminar will be dedicated to questions and comments. So thank you again, Alexandra, for being here with us, and the stage is yours.
Thank you very much. I'm very happy to be here and to be invited to give this talk. Exactly, I'm gonna try to share my screen again. So I think that works.
Yes.
Yes. So I was invited here to talk about one of my teaching papers that I have written. And this paper outlines a protocol of a Bayesian research project that we have conducted a couple of years ago. And the goal of this project was to combine statistical thinking with open scientific practices. And this is what I would like to talk about today. So this is the paper, if anyone is interested in reading it. It was a collaborative effort with the 3 students who participated in the project. It was Anna van der Heide, Trim Tross, and Joran Cornelisse, and my PhD supervisors at the time, Erik Jan Wagenmakers and Martin Marsman. Here are some of the goals that I have for this talk. So first, I wanted to give an overview of this project, the thesis project that is outlined in the paper. I wanted to introduce some of our teaching philosophies and the goals that we had when we were setting up the project. Very briefly introduce the Bayesian methods that we try to teach to our students. I'm not going to go into too much detail here. I'm just going to show you the ideas, the outcomes of the project, and also some considerations for lecturers if they want to set up a similar study, and some takeaway messages that I had personally. So I believe this talk might be interesting, especially for lecturers or supervisors of students who would want to introduce students to some of the Bayesian concepts. Our project was not aimed towards students who have never seen Bayesian statistics before. It was a sort of more intermediate level, I think, the project that we set up. And also for lecturers who would like to balance mathematical training with practical skills, but also the training of good research practices. So how did we come up with our teaching philosophies? We looked at the curriculum guidelines of the American Statistical Association and their personal take on modern statistics education, especially for undergraduate students. And they made 2 points that we thought were really interesting. The first one was that we should not only teach our students statistical methods and mathematics, but we should also teach them the scientific practice so they can actually apply the methods in real life. And the goal of this is to convey a sort of holistic understanding of statistics and to think with and about the data. So not only to be able to solve the equations, but to really understand how to address certain research questions. So that is also something that was the underlying factor of our project. So we had 3 principles that we adopted for our small group of bachelor students who joined the project. The first one was that we wanted to introduce students to the mathematics underlying Bayesian statistics. So what we have found is that in order to make especially Bayesian statistics more accessible to students and undergraduate students, lecturers usually tend to hide the mathematics from the students to give them a more intuitive understanding of the concepts. And we think that is a good approach maybe in the first couple of years of their training. However, when they advance to their master's courses or they become PhD students, they need to be able to actually read this technical literature if they actually want to apply Bayesian statistics in their own work. So we thought that it's good to teach them how to manipulate the different equations and to sort of take away the fear of them to actually use the equations in their work. So that was one of the reasons why we wanted to really look into the mathematics of Bayesian statistics. The second goal, in line with the curriculum guidelines, was to let students experience scientific practice. So in order to achieve that, we wanted to let them apply the methods that we teach them to a real data example. That is why we conducted a little replication study that we analyzed with these Bayesian methods. And we think that especially conducting a replication study is a nice way to teach three Bayesian benefits. The first one was to discriminate between absence of evidence and evidence of absence. If you use the Bayes factor to compare, for instance, a null model compared to a replication model. So that's the first benefit. The second benefit is that it allows students to incorporate prior knowledge, here in the form of the data from previous experiments, to construct a more informative test and to use the prior knowledge to inform their decisions. And the third one is that a replication study allows them to compare the results from frequentist statistics with those with Bayesian statistics. And they can see whether the conclusions differ if you use a Bayes factor versus a p-value. So we thought these are all nice little benefits that the students can take home after they successfully done the project. And then the third principle is that we wanted to convey to the students open scientific practice. Within our department and our teaching philosophy, the reproducibility and replicability are core scientific values. And as we all know, there are like some problems that challenge reproducibility and replicability. This is the flexibility in the data analysis and selective reporting, questionable research practices, then the reluctance to conduct direct replications because it's not novel research, but also a poor availability of data and code. And we thought by letting them conduct a replication study, this is something that they can take also further when they're doing their PhDs. And we also practice some open science skills with these students. So we let them pre-register the study. It was a replication, as I said before, and we let them also share all the data, code, and materials. So they also learned a little bit of documentation along the way. And yeah, set them up for success for future projects, basically. So I'm going to give you just a brief project description so you have an idea of how long the project went. So the name of our project was a Bayesian view on science versus the stars, and I'm going to go into the content of the study in a little bit. It was a direct replication of a study conducted by Wyman and Weiser in 2008, and here, this project was a bachelor thesis project, so a project for undergraduate students. And importantly here is that it wasn't a one-on-one project. I'm not sure how it is in Italy, whether you have like a bachelor thesis and you do it by yourself. Here in the Netherlands, we have sort of small groups of students working together for their bachelor thesis project, so 4 to 5. So this is a project suitable for a small group of students. And the project duration is 4 months with like 22 hours per week as working capacity. We have a little breakdown, a week-by-week breakdown of what we did with the students. It can be roughly divided into 3 parts. We had a part where we reiterated the knowledge and we taught them the Bayesian methods that we wanted them to apply. Then we had a writing and pre-registration phase and also to prepare for the actual experiment. And then the last couple of weeks were just data collection and finishing up the project. So I'm going to go into each of these blocks one by one. So the first one was about reiterating knowledge. So in this block, which was about 1 month, what we wanted to teach the students were specific methods to compute Bayes factors to, on the one hand, test equality constraints. For instance, that one probability is exactly equal as another probability, and inequality constraints. So inequality constraints are expectations of a certain order of parameters. For instance, that one probability is smaller than another probability. So these are the 2 sort of types of hypotheses that we wanted to use for our replication study. And the methods to compute the Bayes factors were, on the one hand, the Savage-Dickey density ratio that we taught to the students, and on the other hand, the encompassing prior approach. And the statistical model that we use were just binomial probabilities. So we chose this because it's relatively simple. When students learn about Bayesian statistics, usually the first example that they see is like some coin tossing example about whether the coin is fair or not. So in our case, the students were already familiar with these binomial probabilities. And that is why we chose that, because then they can focus on the new method without needing to learn a new statistical model. And we chose the 2 Bayes factor methods, the Savage-Dickey density ratio and the encompassing prior approach, because it's very relevant in the psychological literature and replication research, especially hypotheses where it's about a certain ordering of the effects. So in terms of replication research, you can say, for instance, that original authors found that this certain probability is smaller than another one, and you want to replicate this effect, so you're testing exactly this hypothesis. So that is why the encompassing prior approach was so important. So very briefly, just an introduction into the 2 methods. So the Savage-Dickey density ratio might be something that you've heard before when you're dealing with Bayesian statistics. So Savage-Dickey density ratios are used when you're testing exact equality constraints. For instance, whether the probability of something happening is exactly at 0.5, so exactly chance level or not. And in this case, all you need to do is to look at the prior and posterior distribution of your parameter. And then the formula for conducting a Bayes factor is just the height of the prior density at the point of interest. In this case, it would be 0.5 because we're looking at whether a certain probability is a chance level divided by the height of the posterior density at the same point. So by just looking at these 2 points here and the height of the prior and posterior density, you can compute the Bayes factor. So that is something that is very easy to implement, and that is something that students, even on the undergraduate level, can understand. So this was the first method that we wanted to convey to them. And then the second method is the encompassing prior approach. This might be less familiar to you, even if you have done Bayesian statistics in the past, but it is a generalization of the Savage-Dickey density ratio. But instead of looking at an exact equality constraint, like is the probability exactly at 0.5, you're testing an inequality constraint. For instance, that the probability is smaller than 0.5 or smaller than chance level. Here, what you do is that you're not looking at the height of the prior and posterior distribution, but you look at a prior parameter space that is consistent with your hypothesis, in this case that the probability is smaller than 0.5, divided by the posterior parameter space consistent with the hypothesis. So in order to compute the base factor here, what you need to do is to first sample from your prior distribution. And then the only thing you need to do is to look at the proportion of the samples that obey your hypothesis. So in this case, this would be about 50%. And then you do the same for your posterior distribution. You sample values from the posterior, you count the proportion of values that obey your restriction. You put it into the formula and you have a base factor in the end. So this is also something that is intuitive and that can be, for instance, easily implemented in R. So these were the two methods that we conveyed to the student. The next step for them was a little writing period where they pre-registered their study. I think here it's important to say that since we were actually interested in the results of our replication study, we wanted to have a very high quality pre-registration. So we let the students work together on this pre-registration part. They wrote their thesis individually, but this pre-registration was a collaborative effort. And they were also planning the necessary documents and stuff for the data collection, which was then the third part. So this is what I'm going to tell now, a little bit of the background of the actual replication that we did. The students really liked the research question, or they had a lot of fun doing it. So as I said before, the project was called a Bayesian view on science versus the stars. So here you see a little natal chart and the neo-FFE results. And the research question we wanted to address is whether individuals can recognize their own psychological personality descriptions and their own astrological natal charts. So is there a difference between these two? So this is based on work from Carlson, who first did a similar study, and then Weimann and Weiss in 2008. So the procedure of this experiment was as follows. There were 2 time points. In the first time point, participant provided the following information. They answered the neo-FFI inventory. So you can create a psychological personality description based on that. And they also provided their date and place of birth, and then to create an astrological natal chart. And the researchers used the software Astrolabe. Apparently, that's a high reputation software for astrological natal charts. So we use the same one. And then in the second time point, you would give participants 2 things. First, 2 psychological personality descriptions. One was their own, one was from a different participant, and 2 astrological natal charts. One was their own, one was from a different participant. And they had to basically guess which of those are their own. And then the idea is to see whether it's above chance level. I have a little example of how these personality descriptions would look like. Here's an example of the astrological natal charts. It says your emotions tend to rule your thought processes. You have difficulty seeing life objectively. You have an excellent memory, especially about things to which you have formed an emotional bond. You prefer ideas and thoughts that are known and familiar, and therefore tend to dislike fads or radical ideas. The beliefs and traditions of your family and culture are very important to you. Your thinking becomes quite unclear when you're emotionally shaking. So I find that example interesting because it's similarly very specific, but also really vague, which is typical for astrological natal charts. And then an example that might be more familiar to you from the personality description here for the scale neuroticism. So we gave them there's the 9 score and where they fall within the Dutch population. And also a little description that was also based on the neo-FFI. For instance, here with neuroticism, it says you frequently experience negative emotions such as fear, anger, frustration, and sadness. You tend to worry about all sorts of problems, which often leads to stress. You can also be moody sometimes. However, note that a high score in neuroticism does not necessarily mean that you are mentally ill. It just means that you're somewhat more worried and moody than the majority of the Dutch population. So for lay people, these two descriptions might look very similar, but of course for psychologists, this one is much more scientific. So the previous results, so Byman and Weisse, which we used as the original authors, they found, perhaps not surprisingly, that in their sample, almost 80% of participants were able to identify their own psychological profile, but only about 50% could identify their own astrological natal charts, which is basically exactly a chance level. So these authors concluded that the probability to identify one's own profile, psychological profile, is higher than the astrological natal charts. So these are the two, like an inequality constraint hypothesis that I mentioned in the start. So this is not as surprising. More surprising are the results by Carlson that were conducted in the 80s. Here, he didn't give participants 2 options, but 3 options to choose from. And here, 45% of people could identify their own psychological profile and 38% their own astrological natal charts. So what he concluded is that both of these probabilities were approximately the same and approximately a chance level. So he concluded that there was no difference between psychological profiles and astrological natal charts, which we found interesting. So these are the 2 hypotheses we wanted to pitch each other, the Carlson hypothesis versus the Weimann and Weisse hypothesis. And I mentioned 3 goals, or 3 things that our students could learn from applying Bayesian inference in a replication project. The first one was to compare frequentists with Bayesian results. So we let them conduct a reanalysis of the Carlson study. So Carlson's conclusions are based on these 2 p-values. So he basically looked at whether the probability to identify one's own profile is a chance level or not. He found 2 not significant p-values, which he took as sort of evidence for the null, which is that they must be around chance level. This is a statistical misconception in and of itself. So that was something that the first thing that students learned in our project. And the second one is that when they compute the corresponding Bayes factors, the evidence is also not the convincing. So these are the evidence in favor for the null hypothesis. Usually when we conduct research, we take a Bayes factor of at least 10 as a cutoff. So we want strong evidence in favor for the null. These are, these are like very weak or inconclusive and moderate evidence. So we wouldn't really conclude that this is the case, that they're both at chance level and they're both equal. So that was one of the learning goals for the students. And then the second learning goal was for them to incorporate prior knowledge or to use the results from the previous study to inform the current study. And what we did here is that when they were estimating the parameter values or the probability to identify one's own personality profile, they first started out with a sort of flat prior, so they didn't know anything. And then they used the data from the Weimann and Weisse study to update their prior beliefs and get a posterior distribution. So this was the reanalysis part. They just used the data from the previous experiments to get a posterior distribution. And now comes the crux, is that we use this posterior distribution as a prior distribution for the replication. So then we didn't have a flat prior, we had this posterior distribution from Weimann and Weisse. And then with the additional data that our students collected, they received a different posterior distribution. So that was the second learning goal, that they just use the information that's already there, that the field has established, to inform their decisions. And then the last goal was to discriminate between absence of evidence and evidence of absence. And we did this by letting them compute the space factor between this null hypothesis that the both probabilities are equal and equal to chance versus the probability that that correctly guessing one's own personality description is higher than the astrological natal charts. So we let them compute the base factors using the Savage-Dickey and the encompassing prior approach. And based on that, we collected much more evidence than Carlson did. Namely, our results suggest extreme evidence, so a base factor of almost 2000 in favor of our hypothesis that the probability to identify the psychology profiles is higher than the astrological ones compared to the null. So that was the third learning that they had. And here are also the descriptions of what we found. So we only had 29 participants, which is okay for a bachelor thesis. And we collected already a lot of evidence for that. And in there, 86% were able to identify their own psychological profiles, and a bit higher than chance, as 62% were able to identify their own astrological natal charts. Which is interesting, but probably due to sampling error. All right, then, so this was basically the project part. And now what can we take away from this little replication study? So I have a couple of considerations for lecturers if you're interested in setting up a similar project. The first is to be aware of the students' prior knowledge. So at the University of Amsterdam, students are already taking a couple of courses in their undergraduate students for Bayesian statistics. So they already knew what a prior distribution was and a posterior distribution. And they had also basic programming skills in R, which was needed for the project. An alternative, if you're dealing with students that don't have a lot of experience in R, is to do the analysis, for instance, in JASP. They do have a module called Informed Bayesian Binomial Test, where you could actually do the exact test that we did for our study, but just in a sort of SPSS-like click interface. And maybe you need to adapt the difficulty level if you're dealing with students that are not that familiar with Bayesian statistics. Another consideration is to offer enough time to draft a pre-registration. So we gave them almost 1 month to write the pre-registration. And this is quite a lot, but because it was so comprehensive and the students really knew what kind of analysis they wanted to do, then finishing the thesis after the data was collected was really quick. But I would urge, especially if students never did a pre-registration before, to allow enough time to do this. And there are very nice pre-registration templates under Open Science Framework, and there's also a transparency checklist, which is very brief, where students can look at, can see whether they have all the items or all the information included in a pre-registration that's necessary to make it effective. And here, lastly, I have a couple of takeaway messages. I think especially doing these kinds of projects with your students or thesis students is a nice opportunity to practice also for us as lecturers, as supervisors, all these different open science methods. For instance, if you never conducted a replication study before, I think it's a good opportunity to do that with students. Maybe also to practice writing a pre-registration or to using Bayesian inference. The nice thing about bachelor thesis is that there's not really a publication pressure. So we can, sort of use the time also for ourselves to learn these new methods and to dive into them. And mistakes are also allowed, because there's not really a publication on the line if it's your own research. And I also really liked it, this project, that it's adaptable. Of course, the methods that I introduced and the experimental setup can be changed to, for instance, different Bayesian methods that you would like to try out, or any other complex data analysis. The encompassing prior approach seems quite complex, or that is something that the students really had to learn from scratch. And that is why we use the statistical model that is simple. So we only use these probabilities, which is basically the simplest of statistical models, so the students could really understand it. And we didn't want to overload them with like a complex model with a complex method. So we used a very simple case and then introduced these methods, so it's still sort of understandable for the students what's going on, because it's basically just coin flips. And another takeaway message, at least for myself, was that it's good for these student projects to temper your ambitions. So I thought it was a great success, this whole thesis project, because it was such a simple setup. Like the research question is super straightforward. There are not tons of covariates or a complex sort of data structure. And that really allowed the students to focus on what we want them to focus on. So on the statistical methods and really understanding these Bayesian concepts. So that was the main learning experience. So we wanted the experiment to be as simple as possible. And I believe it's better to let students understand or grasp 2 to 3 concepts perfectly rather than to learn many concepts, but then superficially. So that is my last takeaway message. So yeah, thank you for listening.
Thank you, Alexandra, very much.
Thank you.
A very inspiring talk. So, also for the suggestions, of course. So, if there are comments or questions, please use the microphone or report it in the chat. Okay, maybe I can just ask if you also try such a training outside the academics, for example, in the reproducibility network of your country, for example, or if you have suggestions that we may follow to implement such a training in the open science local network.
I think it depends. I think if I would set this up within a reproducibility network, I believe what you ideally want to get out of it is a publication. Otherwise, the people that you're training it with might not be interested to follow through or to actually put a lot of time in the pre-registration itself. So you could think about a research question that might be engaging, but yet still simple enough to learn all these concepts. And then to propose this in the network. You can say like, look, this is the one study we want to replicate. It's relatively straightforward. It's simple. We want to do it in a Bayesian way. You can become co-author of this paper, but then we gonna pre-register it. We're gonna use Bayesian statistics, and we make this into a nice package. So I think if I would set something up like that, I would think about a sort of publishable replication study, if that exists, yeah.
Okay, and also, do you ask for any feedback to your students at the end of the training?
Yes, so since this is already a couple of years ago, I don't know the feedback by heart, but on our OSF page that's within the paper, the student feedback is also published. So there you can read what their opinions were. I think they said that they found the mathematics a bit complicated, but overall they liked the project because it had so many practical but also theoretical elements in there. So I think that is something they really enjoyed.
Okay, thank you. We have a question from Michele Scandola. If you want, you can provide by yourself, Michele.
Okay. Thank you very much for your beautiful presentation. It is very insightful and very interesting too. I didn't know about the encompassing prior approach, so thank you very much. I have a simple question. I mean, I see that I have a very simple question. Generally, with Bayesian statistics, it is a little bit difficult to compute the sample size. Okay, maybe I've just missed that part and you already explained it. But have you computed the sample size for your pre-registration and how?
Yeah, that's a very good question. We also addressed that in the paper itself, actually. You can take different approaches. So for this particular experiment, we wanted to have the same sample size as the original authors, which is not necessarily best practice with the current level of what we know, but we, like Weimann and Weiser had, I think, 52 participants. We also wanted 52 participants, also to make it feasible for the students. We were only able to collect 29 in the given time frame because we didn't have a lot of signups for the experiment. Nevertheless, we got a lot of evidence for our research question. And that is one other Bayesian benefit that you might consider, is that you don't really need power calculations for Bayesian statistics. You don't have this optional stopping problem that you have with p-values. So basically, you can just collect data so long until you get a base factor, for instance, larger than 10, either in favor or against your hypothesis, or until you run out of money and time and you conclude that you cannot really infer something from the data. So that is something that's possible, to just collect data and monitor it and then stop until you reach the evidence that you want to reach. And that can be either in favor or against the hypothesis. There are some, if you, for instance, want to have a base factor of at least 30 or something like that, there are tools out there. It's called Bayesian power analysis or sample size calculator. There's also a reference of that in the paper that you can use, but so far, at least as far as I'm aware, that is only possible for very simple t-tests, but not actually more complex models. So I would recommend setting a criterion for evidence, for instance, a base factor of 10, and just collect data so long until you reach that threshold.
Okay, thank you very much.
Okay, someone else?
I have just, thank you very much. First of all, it was a really, really interesting
Thank you.
presentation and idea. And I was wondering if you've been doing the same kind of work with other students afterwards, or if it changed in any way, I don't know.
Yeah. No, I think this setup is really nice because you have like this small group of students and you can do this kind of replication studies. We found that students find it really engaging. Since then, I haven't conducted a similar experiment, but mostly because I was supervising master students, and those are individual projects. And they need to have a little bit of different criteria. But if I was to supervise another group of bachelor students, I would do a similar kind of experiment. I think it's a good opportunity for them to learn and to also teach them how to write a pre-registration, how to share data, and do these Bayesian analyses. And they have a lot of fun doing it, especially with a research question that they just find funny. So we thought there the motivation was really high. For master thesis students, the students usually come up with their own ideas for research projects. So there, it's a bit more difficult to steer them in such a direction, although I always do with my students Bayesian statistics. I always implement good research practices, let them pre-register things. But to this extent and structured in this way, I'm only able to do that with bachelor students.
Okay, I see. Thank you.
Thank you.
Okay. I think that we can. No, there is another question from Federico Datri. Federico, do you want to directly make the question? Otherwise, I can read
Can
it.
you hear me?
Yep. Yes, we can hear you, Federico.
Can you hear me?
Yes.
Yes.
Okay, thank you. Isn't collecting data until you reach a certain Bayes factor, basically like collecting data until you reach a certain p-value, because they are often related, these two values.
Yeah, so as I understood it, if the null hypothesis is true, and if you collect data, then the p-value sort of fluctuates. And sometimes it's above the 0.05 level, and sometimes it's under. So then this optional stopping really becomes a problem, because you can just look at the fluctuations and then stop at the point that you find convincing, which is, of course, being under the significance values. If you would collect 5 more data points, it might fluctuate back and not be significant anymore. And with Bayesian statistics, that's not the case. Here, when the null hypothesis is true, it takes a bit longer, but usually the evidence will more and more point towards the null hypothesis. So you're either slowly converging to your alternative hypothesis and collect evidence for that, or you slowly collect evidence for the null. And that is one of the reasons why here, or has been argued, that optional stopping is not a problem. And there have been also papers and discussions about this particular problem.
Okay, so we can close the seminar. If you have, I think, if you have other questions or comments, you may contact directly Alexander to the email address alexander.sarafoglou @gmail.com. And so thank you again, Alexandra, for being with us.
Thank you.
And good luck for everything.
Yeah. Thank you so much.
Thank you. So just a couple of information. First of all, for who's required the certificate of attendance, you will receive the certificate within the next 7 days. We remind you also the next seminar on the 3rd April 2004 with Dr. Rose Trappes that will talk about philosophy of open science. And also we will inform you when we will upload the video on YouTube. And thank you to everybody. And let's see next time. Have a nice evening and day. Bye-bye.